In this video, I want to take a few minutes and review some topics having to do with correlation and least squares regression lines and residuals. And this is going to serve as kind of a leap-off point to some hypothesis testing we can do with the slope to show that there's positive or negative association between bivariate data. And also a chance to leap into other kinds of regression, other types of equations. Okay, so a couple of reminders. Correlation. Correlation is a measurement of how strong a linear relationship a set of data has. If the correlation denoted with R is 1, that means there is a positive line that will perfectly fit the, or a line with a positive slope that will perfectly fit the data. The slope doesn't necessarily need to be 1, but the association is positive and every point lies on that line. Correlation of -1, of course, means that there's a line with a negative slope that every data point will fall on. A correlation of 0 simply means there's not a linear relationship. That doesn't mean there's no relationship. It just means the relationship is not linear. The variables can be switched. X and Y can be switched. It's just a measure of how linear the data is. There's no context put to the data, and therefore, with no context, there's no units. It does not mean cause and effect. We've looked at many ridiculous cases where a high correlation may be present, but we could agree that there was no cause and effect there. I think one of the ridiculous ones we talked about was like shoe size and reading ability in school-age kids. Obviously, there's a correlation there, but it doesn't mean that the bigger feet you have, the better reader you are. We'll typically use our calculator to find it. We do it by using the least squares regression piece in our stats menu and by turning the diagnostic on. And the other piece, R squared. Sometimes this is referred to as the coefficient of determination. And this is the percent of variation in the response variable that can be explained by the explanatory variable. And that was one of those definitions we had kind of memorized, kind of those fill-in-the-blank ones. Okay? Now, least squares regression, LSRL, is another thing we need to review and we've talked about. Remember, we used the symbol of a hat. Remember, y hat equals a plus bx, and we always put these things in kind of a context. You know, we had a word here with the hat above it, a plus b times the explanatory variable. So we do need an explanatory and response relationship because we're going to say that a plus b times the explanatory is equal to response hat. We'll use this lin reg on our calculator, and then we can use it to predict. Now, I just wanted to show you what the formula sheet looks like for this. On the first page of the formula sheet that you get when you take the AP exam, you have some things with descriptive statistics, it's called, and what's in here is like the mean and deviation and so on. But down here you see a regression equation, and then it gives you some ways to calculate slope, to calculate the y-intercept, to calculate correlation, and another way to calculate the slope using the sample deviations for y and x. So those things are in there in the formula sheet if you should ever need them. I don't know that you will often. If you did need one, it would probably be this one, that we can get the slope by doing the correlation multiplied by the change in y or change in x, and we use the deviations. Let me also talk about computer output that we have done with this. So if you recall our mini tab output, this is an older problem, obviously. It looks pretty old. This had to do with long jump distances for international competitions, winning times, and least squares regression line. So you can see it will give you R squared, so you could absolutely calculate R by doing the square root of 0.921, but this means that 92.1% of variation in the distance can be explained by variation in year. Next to the constant, this was our coefficient, so next to constant, this was the y-intercept. Next to year, so this was slope. So you would say like distance hat equals 256.576 plus 0.95893 times year. And that would be your way of writing it. And at this point, we hadn't really done anything with these pieces of data, but you'll start to see some things that look familiar, like a T. and maybe a p-value. And these are things we're going to use in the coming days. And finally, residual plots. So residual plots, if you recall, were a plot made with the same x value, and then instead of the y, we use the residual, which is calculated by doing the actual piece of data minus what your line would have predicted. Okay, AP. Or the other way to think about it is actual data is always better and comes first over predicted. This was a great way to judge how good linear regression really fit the data along with your correlation and your R-squared. Trends meant we could do better. You know, a random scattering of points about the horizontal, this is good. This is what we want. A trend means that a different equation would work better. And again, I said this is kind of serving as a leaping off point, because before we'd say, well, another model will work better. Now we're going to ask and try and answer the question, well, what model would work better? What kind of equation would fit better? If a line isn't good enough, what would be good? So residual plots are really useful, and again, they keep the same x values. So for like our previous example, x would still be the year, but the y values would be the residual for each year.